Okay, thank you, Nishant. Good morning, everybody. From one spectroscopy to another spectroscopy. So I'm going to talk about Fourier transform infrared spectroscopy. And it's such a broad technique with lots of application in the food industry. And I learned that one of the most important use that they use, see all your food brands are trans fat content in your stuff that we eat. Most of the trans fat is detected by FTIR. So in that there is proteins, you can detect proteins, pharmaceuticals, organics, very, very broad technique that has been used for a lot of different types of materials that uses the idea that infrared light, and when you subject materials to infrared, certain bonds vibrate in a different manner, and you can pick up that energy of vibration and understand what actually that bond is. And looking at what that bond is, you identify what material it is. So that's a basic idea. It's infrared spectrum, so larger wavelength, lower frequency as compared to visible spectra, your regular light. Okay, so most molecules absorb light in the infrared region and converts it into molecular vibration. And absorption is measured as a function of wavelength or wave numbers, wave number being the inverse of wavelength. And that spectrum serves as a typical molecular fingerprint. Like in any spectroscopy, you get a spectra that is time domain, convert that into frequency domain with Fourier transform, and that's why you get a frequency domain spectra, which you convert into wavelength and then invert it to wave number so that you can have the peaks and valleys clearly marked and you can relate everything as a function of wave number. And it also collects all the wavelengths in one pass, so that in the infogram should be first Fourier transform to produce intensity as a function of wave number, or if you do it one each, then you have to stitch all these spectra together and see where the peaks are, but then the software automatically does it for us by doing the Fourier transform. So what does electromagnetic radiation do to molecules? If you look at what is happening, so from a lower energy, the nuclear spin transitions in the radio wave frequency to microwave, there is rotational motion. Infrared is vibratory motion. Near ultraviolet is electronic transitions. X-rays, gamma rays, ionized materials. So you basically have the whole spectra of energy, and you'll see the energy on the blue scale. 10 to the 6 kilocalories per mole for gamma rays, where you really have ionization and effects beyond that. And for infrared, about 1 kilocalorie per mole, which are basically the molecular vibrations. So, again, infrared radiation is largely thermal energy, and it induces strong molecular vibrations and covalent bonds. One of the ways that civil engineers like to look at is to look at it as a spring connecting two different atoms or two different molecules or whatever, and a force is applied, whether it stretches or compresses. You basically measure the quantum of that force, and of course you relate that to energy. There's actually a very nice picture which I like to talk about how it does symmetrical stretching versus asymmetrical stretching versus rocking versus bagging. Again, this is two dimensions, so some of those things are not very clear. But what we use most in cement-based materials or binders that we normally talk of are the symmetrical and antisymmetrical stretching of the bonds. So how does the bond stretch? Whether that they stretch symmetrically, asymmetrically, what is the extent of stretching from which you can infer what are the characteristic bonds and therefore what the material actually is. So characteristic vibration depends on the bond length and the atomic mass. So once you have the idea of that, the energy can easily be related to those vibrations. So if the energy of the infrared radiation matches the energy required to start one of those molecular vibrations, then infrared is absorbed. Because only if it is used to do that absorption would the energy be used, otherwise it will just get reflected, it will have no use of it. So you have a certain fingerprint, we call it the fingerprint region of IR, where you initiate those molecular transitions. And this is a simple picture of what it does. You have a mirror, a fixed mirror and a movable mirror. Data comes from the fixed mirror, radiation that comes through the fixed mirror and the movable mirror. Once you start moving one mirror, that is a different wavelength that you can start to collect all simultaneously. So if you have only one mirror and the movable mirror also is in one position, you are collecting only one wavelength. When you move that movable mirror in different locations, that's where you get the entire wavelength spectra, you get the detector, you get the interferogram that's converted into a Fourier transform with a spectrum that gives you the intensity as a function of wave number. There are several sampling techniques. So you have the transmission method, which is a popular method, or has been a popular method, but not that much of use now. There, the transmission energy is just measured. You have to have the sample. If it's a powder, made into a pellet, potassium bromide is usually used to mix the sample because KBr is IR transparent, so you get a good reflection or good transmission. But then attenuated total reflection systems have come into practice. There's lots of ATR, FTIR systems now where the beam is directed into an optically dense crystal, which is generally a diamond crystal, with a very high refractive index, and that reflectance creates an evanescent wave. I probably have a picture of the next one. Reflectance that creates an evanescent wave that is detected by the detector. So now you don't need to prepare it with KBr. You can just put your powder in on the ATR holder and then have smooth contact between ATR holder and your sample holder. And then there is diffuse reflectance also, where you can still ground into a fine powder mixed into potassium bromide, but ATR is the gold standard these days. So in ATR, IR travels through a crystal. It's totally internally reflected Bragg's law and at the sample interface, and the reflected light travels to the FTIR detector. And then during that internal reflection, part of the light travels into the sample that is getting absorbed into an evanescent wave as a sample, and the penetration depth of the wave is defined by the refractive index difference between the sample and the ATR crystal. If it's diamond crystal, known value, that refractive index difference is an indication of the intensity of the wave that goes in. So now you can use this idea to identify several things in the spectrum. You can do identification of substances, and then if you actually start to do calibrations with known values, the intensity calibration, you can also find out how much of material is present. But in materials that have very, very known chemistry, things don't change much. This calibration is very useful, but in systems that changes with time, changes with so many different things, environment, calibration for quantification is slightly harder. So here is some interesting FTIR spectra, and I'll come back to this a little bit later. So you have, if you look at this, is hydrating slag with time, with different times, actually activated slag. So you see something around 975 to 980 that changes with time. That is a vibration of the SiO tetrahedron. The ALO octahedron vibration is about 480. You have a hydroxyl, very heavy peaks of water that is happening at about 3600. So if your sample has lots of moisture, you will see very sharp, very big peaks there. And then there is OH for water, there's carbonate peaks that happen around 1420, 1425. So these are all characteristic signatures from which you can find out what the material is. But again, you look at it and you say that, okay, where do I know where the peak is, right? There's such a broad peak. Where do I find out? Your instrument generally gives you where it thinks the peak is, but it has lots of problems when you deal with very heterogeneous materials that we are dealing with. But generally the idea is, therefore, yes, we can use it as a qualitative method, understand where those peaks are, understand what those preliminary predominant bonds are, and say that, okay, do I have aluminum replacing silica in tetrahedron? Do I have SiOAl from SiOSi? So we can do some of those quantification that happens with time. So I've listed here some of the bands that you typically see when slag is activated by sodium or potassium silicates. The cationic effects on activation also is significant that we pick up from FTIR. So you have hydroxyl groups, stretching of CO3 carbonate bonds, CO bonds happen at about 1400. SiOT, T could be Al or Si. So SiOSi or SiOAl, that happens in the 900 to 1000 centimeter to the -1 range. That's your typical signature for those materials that are rich in silica. And then you have shoulder bands of non-polymerized orthosilicates, and you can see that with the changes in the wave number associated with that peak, you can figure out what the degrees of reaction is. And you can use the same idea for fly ash activated using alkali sulfates. You can see the SO bond vibration at 1090 when lots of heterodyte is formed with sulfates. Again, you need to make sure that all of these are calibrated with some other technique that you are actually sure there is that. Say 1090 can be heterodyte, 1090 could be so many other bonds that could get interfered with this. But based on what we know in our materials, it's fairly sure that these are heterodytes. When you do carbonated binders, when you start to do carbonate binders, you can see here class C and class F fly ash mixed with portlandite and carbonated. So portlandite has a very high carbonation efficiency, so you can actually start to get much more carbonation than in cementitious systems. So, and you get pretty good strength with such binders. So pure fly ash or portlandite blends, no cement at all. And you can see the CO3 bonds, the in-plane and out-of-plane carbonate vibration to understand how much of carbonates are formed. But the idea is that, again, this will require the operator to understand the material, and even when you understand, if it's a complex heterogeneous material, there are so many different things that are going on. So several types of silicates and aluminosilicates are there in many of those systems. Some of them, if you look at identification, the bonds are, the energy is very close to each other, the peaks appear very close to each other, sometimes broadening the spectra like you're seeing, right? So even the energy is never sharp in any of those spectroscopy techniques, because what you are getting is generally an overlap of many different processes. So that sometimes could lead to incorrect understanding. You probably have used NMR spectroscopy to refine and understand. But what we have done is a Fourier self-deconvolution process. So we basically say that, and that's in a very small range from about, 1600 to 1700. So just about 100 centimeter to the -1 wave number, and you see that spectra, which is a very broad spectra, and now we can start to look at, is it just one spectra or overlapping of different bands? Now, anytime you get these spectra, these are all signatures that are coming out of different processes. So there's something called line broadening for all these spectra, and that is very similar to the idea that there is an uncertainty in the energy that you predict or measure, and there is an uncertainty in the lifetime of that vibration because of that energy. So very similar to Heisenberg's uncertainty principle, and this is related to Planck's constant. So you can have this lifetime broadening. Depending on what the state of energy is, you will get broad or narrow curves, and you just have no idea that what kind of bond characteristics are possible. So you need to deconvolute this, and the deconvolution is a problem. If you've done NMR spectroscopy, deconvolution for NMR spectroscopy is very simple, because the deconvolution of a Lorentzian shape with another Lorentzian shape gives you a Lorentzian shape. You don't have to do anything. But now, if you assume a line function to be Lorentzian, then you're doing a multiplication function here, because it becomes exponential after that. So then there are several different complications. So we use either a Gaussian or Lorentzian as a line shape function. Again, these are simple exponential mathematical functions to predict what that shape is. To do the width of the curve, you do something called full width at half maximum or half width at half maximum. One of those parameters to define the curve is basically your bell-shaped curve with different probabilities defining different standard deviations and stuff like that. So you use that, and so if you use an experimental spectrum, I can use that as an actual spectrum times a line-shape function. So that's what I was talking about. It becomes a multiplication, and therefore I can do a line-shape function to do this. And therefore, and then of course after you do that, you do an inverse Fourier transform. Now it's very easy. MATLAB has built-in functions to do all of these once you give the data. So it's not as complicated as the equations look like. If there were no tools, nobody would have done this. But you can do an inverse Fourier transform to find out what that is. And then in Fourier, inverse Fourier transforms are always periodic infinite, which means you have to truncate it at some point in time. The user should know where to truncate that. So there's lots of user input and the knowledge of the system that you're dealing with required if you're doing the self-deconvolution process. And then you augment that with standard curve fitting algorithms, and you now start to deconvolute this one big band that you see from your FTIR instrument into multiple peaks that you can attribute to different bond vibrations. So here is deconvoluted spectra. And you can actually now look at SIO symmetric and antisymmetric stretching bands, which are together in the actual Fourier transform spectra. Once you start differentiating it, you will know which one is increasing in magnitude, which tells you, is aluminum being incorporated into the SIO structure or not? Are you still getting, once the reactions are done, are you still getting a quartz structure, and of course with some connections giving you the strength, or is aluminum really replacing silica in the tetrahedral structure? Right? You can do that. I mean, with NMR you can do this, but NMR will take you way more time, much more requirement in terms of analyzing and interpreting results with respect to Q0, Q1, Q2, all of that. Alkali cation effects, we also can see how that SiO-Al and SiO-Si bonds change because the bonding force constant when aluminum replaces silica in the tetrahedral structure is much lower than in an SiO-Si structure. Bonding force constant is low, meaning the energy of vibration also is low. We can figure that out and use that to understand where is the wave numbers trending and how much of replacement there is. So, quickly, we can do better inferences of the activator type, reaction time, temperature, lots of different applications. Rapid increase in wave numbers could be used to look at what the temperature does to the process. Now, if you're doing it initially, it's always a good idea to make sure that you can calibrate it with NMR spectroscopy to actually see that, yes, whatever reactions I'm predicting, I'm actually seeing in the form of Q1, Q2, Q3 structures from non-polymerized silica to polymerized silica as you get to. So Q2 is what you see in your regular Portland cement structures, Q1, Q2, Q2, Q3 in alkali activator structures, Q4 is the polymerized silica species. So you can have FTIR coupled with NMR or a good deconvolution strategy as a standalone method to look at changes in reaction sequence, product formation. But it's a very useful, very quick technique. I mean, if only identification is your concern, you don't want to quantify, you don't want to understand all of these finer details, you want to find out, is my system carbonating? Has it carbonated? Or do I have polymerization trends in the direction that I'm thinking of as I use 1 molar sodium hydroxide to 10 molar sodium hydroxide to activate something. Those are very easy and very straightforward, but once you start to find out which one is actually doing it and how is it changing, it requires a little more of